Today we're going to be looking at a number of topics. Many of these you have heard about from previous classes in physical science. We're looking at atomic structure. We know that an atom is made up of smaller particles. These particles are the protons, the neutrons, and the electrons. We want to look first at a definition of three terms. Atomic number. The atomic number is defined as the number of protons in an element. Now, you may think, well, isn't it the number of electrons? Only if that atom is neutral. If the atom is neutral, it would have the same number of positive and negative charges, protons and electrons. However, we've been studying ions, atoms with a charge, because they have either lost or gained electrons. Very strictly, the atomic number is defined as the number of protons in an atom, and it is the number of protons that identifies that atom. If you're looking at a periodic table, and you're looking at certain atoms on the periodic table, hydrogen, the first element on the periodic table, has an atomic number of 1. It has 1 proton, and the neutral atom has 1 electron. Carbon has 6 protons, and the neutral carbon atoms have 6 electrons. Aluminum has 13 protons. So the atomic number tells you the identity of an element. The atomic number for an element does not change. If you change the atomic number, you have a different element. Mass number. The mass number is the number of protons and neutrons. Now, if you're looking at subatomic particles, I hope you remember that protons are positively charged. They are found in the nucleus. Not only are protons in the nucleus, there are neutrons. Neutrons carry no charge. So we have protons and neutrons in the nucleus of an atom. Protons and neutrons both have mass. All matter is defined as something that has mass and occupies space. The mass of the proton is very similar, but one is slightly larger than the other. The neutron is slightly larger. So we have protons and neutrons in the nucleus. Now, if you're going to count the number of protons and neutrons in the nucleus, that would give you the mass number. Since you're counting objects, things, this number is always going to be a whole number, and it has no units. So looking at your periodic table, let's take a look. If you were to look at carbon as an example, carbon has an atomic number of 6. You see that number in the upper left-hand corner on this periodic table. Now, where is the mass number? It's not really there, but you can obtain the mass number if you look at the number in red in the upper right-hand corner. You see 12.0107. Well, that's not a whole number, but if you were to take that number and round it off to the nearest whole number, which would be 12, that is the mass number for carbon. So, if you were going to take the mass number, which is the number of protons and neutrons, and you were to subtract the atomic number, which is the number of protons, then you would obtain the number of neutrons. So you can find the number of neutrons for any atom on the periodic table. Let's take a look at your periodic table. Looking again at the periodic table, let's just try aluminum as an example. If we have aluminum, aluminum has a mass number of, well, we would round that number off to 27. 27 is the total number of protons and neutrons. And it has 13 protons. So if we take 27 and subtract 13, for aluminum we have 14 neutrons. You can do this for any atom. So we now see that we have the number of protons, neutrons, and if we have a neutral atom, that's the same as the number of electrons. The electrons are going to have virtually no mass. In comparison to protons and neutrons, the electrons are very small. They do have mass, but the mass is negligible compared to the mass of the other subatomic particles. Quite often we refer to the mass of the electron as being zero, even though we don't mean zero, nothing. There is a small mass. They are associated with the electrons. The next term that we want to look at is the atomic mass. This is the mass of an atom. Duh, sounds like that from the very word atomic mass. But you know that an atom is way, way too small to mass. So how do we get the mass of an atom if we don't have a balance that we can put it on and weigh? Well, we're going to compare it to other atoms. We're going to compare one atom to another, to a standard. And that standard is going to be carbon-12. Now, why do I say carbon? Well, we looked at a number of different atoms as possibilities. What would you want to compare it to? We'll discuss that in class. But the element they decided upon was carbon, because it is the basis of all life as we know and understand it. The problem is that carbon's got some problems that we have to talk about. Let's look at these atoms. We'll start with hydrogen. And you see that in this notation, I've listed the number of protons, the atomic number, which is 1, in the lower left-hand corner. Well, when you designate hydrogen, there are different forms of hydrogen that exist. Hydrogen 1, hydrogen 2, hydrogen 3. This top number in the upper left-hand corner is the mass number, the number of protons and neutrons. So if you take the mass number, the top number, subtract the lower number, the atomic number, you get the number of neutrons. This form of hydrogen has 0 neutrons. 2 minus 1. This form of hydrogen has 1 neutron. 3 minus 1. This form of hydrogen has 2 neutrons. What do we call these? These are called isotopes. An isotope is something that varies in the number of neutrons. And because it varies in the number of neutrons, it varies in mass, because neutrons have mass. This is the only element where the isotopes have been given names. The names for these isotopes are protium, deuterium, and tritium. Tritium is radioactive. And the most naturally occurring form of hydrogen is protium. Carbon also has isotopes. The 2 isotopes of carbon that we're just going to talk about as possibilities, even though there are more isotopes of carbon. Let's look at the most common form of carbon, which is carbon-12. But there is a radioactive form of carbon called carbon-14. That's what we use in radioactive dating. Uranium, atomic number 92 on the periodic table, is another example. Uranium-235 and uranium-238. Can you determine the number of neutrons in all of these isotopes? You should be able to. You'll be asked to on tests. Well, we wanted to determine the atomic mass, and we decided we'd compare it to carbon, but which form of carbon? There's two forms. Carbon-12 is the most naturally occurring, and so we're going to compare it to a form of carbon, carbon-12. And how much does that atom weigh? Well, you can't weigh it. So what we're going to do is say that carbon-12 has an assigned value. Wrong board. Has an assigned value. So the atomic mass is going to be defined as the mass of an atom relative to a standard. And that standard is going to be carbon-12. Now, this isotope of carbon is going to be assigned a value of exactly 12 AMUs. Assigned a mass of 12 atomic mass units, AMUs. Now we're going to compare all other atoms to this carbon atom. How are we going to do that? Well, this is going to allow us to determine the actual number for the atomic mass on the periodic table. Let's take an example. Let's say that all the carbon in the world was carbon-12. Then the number on the periodic table for the mass of carbon should be carbon-12. But what if there was another form, carbon-14? And let's pretend all the mass of carbon-14 in the world, all the carbon in the world, was carbon-14. Then the mass on the periodic table would be 14. What would happen, however, if what was found in natural supplies of carbon were a 50-50 mixture, half carbon-12, half carbon-14? What number would appear on the periodic table for the mass of carbon? Well, the periodic table takes into account all forms of carbon and their relative abundance. So if all we had was carbon-12 and carbon-14 and they were there in 50-50 percentiles, the number on the periodic table would be 13. So this is how we're going to calculate the numbers on the periodic table. What we're going to do is we're going to take the mass of the atom, multiply it by its natural abundance, how frequently it occurs in nature. This is going to be written as a decimal, and get some number. We'll do this for each isotope, and then adding them together, the sum is going to give us the number found on the periodic table. We'll try this in some handouts.